Hi students, in today's session I am going to discuss crystal field stabilization energy values, magnetic moment and electronic configuration in coordination chemistry. So we all know strong ligands, weak ligands, spectrochemical series in previous video I had explained. So in strong ligand is there, crystal field stabilization energy is more. Weak ligand is there, crystal field stabilization energy is less. That means simply you try to understand. If strong ligand is there, splitting is more, splitting gap is more. Splitting gap is more. If weak field ligand is there, splitting gap is less. So this is a degenerate orbital, students. D orbital. D means how many? Five-fold degeneracy, right? So whenever ligand is approaching, then what happened? Degeneracy destroys and split into two parts, e.g. 2,2G set and EG set. Out of 5 orbitals, 3 in lower energy and 2 in higher energy. Why this is lower energy, students? In octahedral splitting, this is octahedral splitting. In octahedral splitting, along the axis ligand is approaching. That's the reason, e.g. doublet is nothing but dx square minus y square dz square. So and this is what triplet is nothing but dxy, dyz and dzx. So along the axis ligand is approaching. That is the reason EG set energy is more. EG set distracting more. So finally, so what is the result here? EG set has higher energy and 2,2G set triplet has lower energy. Along the axis dx square minus y square dz square. So I am drawing the structure here to understand more better. See, dx square minus y square I am drawing. Imagine this is x-axis, y-axis, y 2 times and x again 2 times. Okay, along the axis. Whenever ligand is approaching along the axis, what happened? It effect is more. So it effect is more. That's the reason EG has higher energy when compared to 2,2G in octahedral complex. In tetrahedral complex, along the axis octahedral complex, in between the axis dxy in between the axis, like this. Yz means y, this is x-axis, y-axis. Yz means yz, you can take it. Z means zx means zx, you can take it. So it is in between the axis. So in between the axis approaching is their ligand. Then a 2,2G set effect is more, that is more energy in tetrahedral splitting. In octahedral splitting, why EG set is greater energy? Because the ligand is approaching along the axis. So finally, this is the crystal field splitting diagram. Here I am giving more importance for the competitive. So weak field ligands, strong field ligands, electronic configurations and crystal field stabilization energy frequently asking in JEE and mains, that JEE and NEET examination, that I am explaining to you. See, 2,2G EG. So finally, what is the conclusion? Strong ligand is approaching, strong ligand effect is there, then more energy gap. So a weak field is there, less energy gap. You can remember like this. Okay, this is out of 5 orbitals, 3 orbitals lower, 2 orbitals upper. Next one here also, one is down, one is up. Okay, 2,2G EG. So this is energy gap less, energy gap is more. Next, filling electrons. I am explaining here only. After that, I will give you table for you students. So once you look into the table, easily you can understand remaining points. Suppose in my hand, one electron is there. One electron, D1 configuration is there. Here one electron, it will fill. In two electrons is there, it will fill here. And 3 electrons are there, it will fill here. Okay, it follows Hund's rule. Even weak field ligand also, D1 you can take it 1 and D2 you can take it, this is also 1, and D3 you can take it, this is also 1. There is no problem. Strong ligand, weak ligand, D1, D2, D3, there is no issue, there is no problem. Now D4 configuration, here also D4 configuration I am writing. D4 configuration time, students, listen carefully. And D4, that means electrons either here filling and then jumping, depends on the ligand, depends on the crystal field stabilization energy. If energy gap is more, the splitting energy gap is more, then what happened, instead of jumping, pairing will take place here. In strong field again, pairing will take place because energy gap is more, instead of jumping, pairing. But whereas weak field again, energy gap is less, then what happened, so it jumps here. This is the difference. So finally D4 configuration you can tell here 2,2G, 2,2G, 4 and EG 0. And what about here? 2,2G, 3, EG 1. Did you understand what is the difference between strong ligand, weak ligand electronic configuration? Similar way, excuse me, similar way you can take it D5. D5 means here pairing, D5 means here it will come, and D6 means here pairing. So D6 means down pairing. So like that it will take place, students. Here it follows completely Hunt's rule, first filling then pairing. But strong ligand, weak field ligands, is there a difference? Did you observe? Strong ligand is nothing but energy gap is more, instead of jumping, pairing will start. Weak field ligand time, what happens, students? So instead of pairing, jumping will go. So finally, based on this electronic configuration, I gave table to you. Look into this. Yes, D1, D2, D3, no problem. D1, D2, D3. Here EG 22G1, 22G1, EG0. So same thing here. Next D4. Just now I had explained 22G4, EG0. Here 22G3, EG1. And D5, 22G5, EG0. So like this. Slight difference is there. And the down one also it's same. D1, D2, D3, no problem. And the next one. See, I'll show here points. D8, D9, D10 also no issue. D8, D9, D10 also no issue. Only issue with D4, D5, D6, D7. Clear, students? Here D8 also same thing. D9 also same thing. D10 also same thing. Only the problem is D4, D5, D6, D7. 1, 2, 3, 4. Here also D4, here different, here different. Here different, here different, here different. See, depends on energy gap. Energy gap is more, strong ligand time. Then what happened, instead of jumping, pairing will take place. Weak field ligand time, what happened, energy gap is less. Then what happened, instead of pairing, jumping will take place. It's very easy to write electronic configurations. Clear, students? After that, see, 22G2, 1 means how many unpaired electrons? 1 unpaired electron. Here I had given unpaired electrons also they are asking, 1 unpaired electron. Here also 1, here 2, up to here no issue. Here 22G, 22G4. 22G4 means how to write, students? 22G4, 1, 2, 3, 4. See, 2 unpaired electrons, 2 unpaired electrons. 5 means 1 unpaired electron. 6 means you see 6 means no unpaired electron. So EG also 0. This is 1 unpaired electron. Like this we have calculated unpaired electrons. Here D4 you can see, students, D4 what happened here? This is 2G set, this is EG set, right? So less energy gap, because of this what happened, D4 1, 2, 3, 4, right? See, 1, 2, 3, 4, right? So next here you can write how many unpaired electrons? 4 unpaired electrons we have got it. D5 means 1 more it will come, 5 unpaired electrons. D6 means it's pair, no? It's pair. Pair means 4 unpaired electrons. D7 means your pairing and 3 unpaired electrons, like this. D8 means 2 unpaired electrons. D9 means 1 unpaired electron. D10 0 unpaired electrons. Like this we are calculating. N equal to unpaired electron. Finally understood the point, I think. Okay, hope clear everyone. Now I have written conclusion points here, students. D1, D2, D3, D8, D9, D10, same electronic configurations. same electronic configuration, whether it is strong field ligand and weak field ligand also, no issue, no issue. And D4, D5, D6, D7 only changes is there. Strong field is nothing but pairing will go, and weak field is nothing but filling and then jumping. Instead of pairing, jumping takes place. Okay, that's it. Next, afterwards, magnetic moment they are asking. Magnetic moment equal to root over n into n plus 2 Bohr magneton. Detailed explanation I had given in D and F block elements. If you have any queries, please go through the D and F block elements video, students. So I give shortcuts also. If n equal to 1, what is the answer? Mu equal to 1.73. That's it. That's it. N equal to 2 unpaired electrons. Then what happens, students? N equal to 2. Then 2.8. 2.8. Then N equal to 3. Magnetic moment is 3.8 Bohr magneton. That's it. N equal to 4. N equal to 4. Mu equal to 4.8. So 5.8. Mu 5.8. They'll ask sometimes questions like this. Mu equal to 5.8 Bohr magneton. How many n value? How many unpaired electrons? How many unpaired electrons? How many unpaired electrons, students? If mu equal to 5.8 Bohr magneton, then same number. First, what is the number? First, what is the number? That is your answer. That is your answer. That's it. So here n equal to 5. You will get questions like this. Now you can see points. I have written unpaired electrons here, right? See, I have written unpaired electrons. You can go like this. You can go like this. Okay. So 4.8, 3.8, 2.8, 5.8 like this. Highest magnetic moment in which case? Lowest magnetic moment which case? More number of unpaired electrons. Color, colorless like that. They'll ask. Unpaired electrons only responsible for showing color also. No? Okay. Now next one. Crystal field stabilization energy calculation. One or two examples I will give. CFSE. CFSE. So this is also one of the important questions, students. Here 2G. Okay, D4 configuration is there. D4 configuration. For D4 configuration, write strong ligand. Strong ligand they will ask, or else they will ask you one more question. Low spin complex. Low spin complex. Strong ligand is nothing but low spin complex. Now, what is the configuration? 2G, 2G. What you will get here? 2G4 and Eg0. Then crystal field stabilization energy equal to, what is the value, students? Minus 2 by 5 into 2G plus Eg into, what is this? 3 by 5. So then what you will get here? 3 by 5 into Eg. That's it. Now calculate. Everything is here only. You can calculate. See, 2 by 5. 2 by 5 is nothing but how much value, students? 0.4 into 2G. How much? 4. Plus 3 by 5 into 0. So this is finally 0. This is minus 1.6. What is the answer? Minus 1.6 delta naught. Octahedral splitting. Octahedral splitting. Next one. Another question. D6 configuration. If you will take D6 configuration, then what you will get? 2G. What you will get? Eg. So first filling, then pairing also, no? So then finally 2G6, Eg0. Eg0. Then calculate crystal field splitting energy. Then what is this? 0.4. 0.4 into 6 plus 0.6. 0.6 into 0. So finally what you will get here answer, students? What you will get answer? Simplify and tell. 1.6. That's it, answer 1.6 delta naught. 6 4s are okay. Sorry, 1 second. We'll simplify this one. 0.4. 0.4 into 6. 6 fours are 24. 6 6 are 2.4. Yes, what is the answer here? Minus 2.4 delta naught. That's it. Now, suppose weak field ligand is there. This is strong field ligand. Strong field ligand, crystal field stabilization energy. Remaining everything you can calculate like this. Now, suppose weak field ligand is there. Weak ligand is there, and they will mention here high spin complex also sometimes. High spin complex. Next one, outer orbital complex. Low spin means strong ligand, inner orbital complex. Here outer orbital complex. Can you write this one? What is this configuration? Suppose if you have taken D4 configuration, what you will get? 22G, 22G, EG, 22G3, EG1, 22G3, EG1, right? So that's it. Now calculate this one, crystal field stabilization energy. Do you remember 22G3 down filling, then instead of pairing, jumping will go, because weak field ligand crystal field stabilization energy equal to minus 0.4 into 3 plus 0.6 into 1. Then what is this? Minus 1.2 plus 0.6. Finally, we will get minus 0.6 delta naught. 0.6 delta naught. Like this we can calculate. Okay, D8, D9, D10, no issue. And next one more I am giving. Last question. Here D5 configuration you can take it. 22G, what happened here? 3 EG2. Crystal field stabilization energy equal to minus 0.4 into 3 plus, what is it students? 0.6 into 2. This is what 3 4s are 12, 1.2, 1.2 plus this is 1.2. Then what happened here? It is crystal field stabilization energy equal to 0. It is 0.